Another area of mathematics in which totally non-negative matrices appear is the study of the locations in the complex plane of zeros of polynomials and poles of power series. If we're given a sequence, let's say an, and goes from 0 to infinity, we can define the Toeplitz matrix T of that sequence by writing the sequence down in the first row and then writing it down in the second row but shifted one over. Etc. This is an infinite matrix. And it's upper triangular, so all zeros below the diagonal. Let's let Tm of C be the ring of infinite Toeplitz matrices. So with addition and multiplication, just defined by matrix multiplication, matrix addition. It turns out that this is really nothing more than the ring of formal power series in X with complex coefficients. I'll let you prove this for homework, but let's do a small example so we can see. And maybe I'll restate this proposition. So this is basically saying that the infinite Toeplitz matrix corresponding to sequence AN times the infinite Toeplitz matrix corresponding to the sequence BN equals the infinite Toeplitz matrix corresponding to the sequence Cn if and only if this power series times this power series equals this power series. And then addition is sort of obvious. We're just adding components. So multiplication here corresponds exactly to multiplication here in the ring of formal power series. So for example, let's take some very short sequences. Let's look at the sequence 1 alpha 1, and 1 alpha 2. So the power series here are just polynomials. 1 plus alpha 1x and 1 plus alpha 2x. And we have 1 plus alpha 1x times 1 plus alpha 2x equal to 1 plus alpha 1 plus alpha 2x plus alpha 1 alpha 2x squared. And then if we look at the product of matrices, T of 1 alpha 1 times T of 1 alpha 2 equals, we've got this matrix that has 1 alpha 1, 1 alpha 1, etc. and zeros elsewhere, times a similar matrix with 1 alpha 2 and zeros elsewhere. If we multiply this, then in the 1, 1 position we get 1, 1 plus 0 plus a bunch of zeros, and then alpha 2 plus alpha 1, and then in the third position of the first row, 0 plus alpha 1 alpha 2 plus 0, and then after that we get 0 times 0 plus 0 times 0, everything. We get all zeros after that. And then if we do this in the second row, we get 0 plus 0 is 0, and then we get 0 plus 1 plus 0 is 1, and then we get 0 alpha 2 plus alpha 1, and then we can see that we just keep getting the same thing. So multiplying the power series, which in this case are just polynomials, is equivalent to multiplying matrices. So since we're studying total non-negativity, the natural question to ask is, for which sequences an, n going from 0 to infinity, is the infinite tuplets matrix totally non-negative? This question was answered in 1952 or so. I'm writing a tiny bit high. It was answered by Aissen-Schoenberg and Whitney. And this Whitney is Ann Whitney again, who was the author of the other theorem that we had in the last video or a couple of videos ago. And the theorem says that this infinite tuplets matrix is totally non-negative if and only if the power series an x to the n has the form one plus alpha I x, product as I goes from 1 to some number d, over another product of 1 minus beta I x times exponential of gamma x for alpha 1 through alpha d, beta 1 through beta k, and gamma all real numbers, all non-negative real numbers. One direction of the proof is kind of long, so I'm going to omit it. So that is this direction. But this direction is kind of short and cute, so we'll look at that. So let's suppose that these numbers are all real and non-negative. Now by the proposition which asserts the isomorphism of Toeplitz matrices and power series, we can look at each of the factors in this expression, and if we can prove that the Toeplitz matrix corresponding to that factor is totally non-negative, then we know that the product of totally non-negative matrices is again totally non-negative. Oh my god, look at this glare. So suppose that this is alpha 1 through alpha d. You can read the betas, and then you can't read this word, but I will just put it on the next line. So by the proposition, that is that Toeplitz matrices are isomorphic to the ring of power series, it suffices to show that the Toeplitz matrix of 1 alpha, so those are the coefficients of 1 plus alpha x, and the Toeplitz matrix of 1 beta, beta squared, beta cubed, etc. Those are the coefficients of 1 over 1 minus beta x, which is 1 plus beta x plus beta squared x squared plus beta cubed x cubed, etc. And the Toeplitz matrix of 1 gamma, gamma squared over 2, gamma cubed over 3 factorial, etc. If we can show that those 3 matrices are totally non-negative, that's sufficient. Alright, so I'm going to show a path matrix for each of these. So actually I'm going to show a planar network which has each of these matrices as a path matrix. And I can say T1 alpha is the path matrix of and I'm going to number sources and sinks from top to bottom instead of from bottom to top as I usually do, because it's just easier to put the dot 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 at the bottom. So if we have this repeating pattern where we have a diagonal edge of weight alpha, and then horizontal edges are all weighted 1 and the arrows all go to the right, then from source 1 to sink 1 we have 1 path. From source 1 to sink 2 we have 1 path of weight alpha. Then from source 1 to sink 3 we have no path, because once we take this path labeled alpha down, it's too late to go back and take this other one. And then if we look at the second row, so from source 2 to sink 1 there's no paths. From source 2 to sink 2 there's 1 path of weight 1. From source 2 to sink 3 there's 1 path of weight alpha. And then this is just like it was above, because the graph is periodic here, so we're just going to see the same things happening over and over. Alright, so now we need to have a planar network whose path matrix has 1 beta, beta squared, beta cubed, etc. in each row. So T of 1, beta, beta squared, beta cubed, beta the fourth, etc. is the path matrix of a similar matrix. So we have these horizontal edges all weighted 1. And now I'm going to have a single vertical edge of weight beta going down, and it's going to be placed so that when we take one, we can still take another one of them. So again, all the horizontal edges are going from left to right. And then the path matrix, which I'll draw over here. So from 1 to 1, we've got a single path of weight 1. From source 1 to sink 2, we have a single path of weight beta. From source 1 to sink 3, now it's possible to do that because we can take the beta edge and then take another beta edge. If we do that, then we've got a weight beta squared. And then from source 1 to sink 4, we've got one path of weight beta cubed, etc. Now from source 2 to sink 1, there's no paths because this edge is oriented downward. From source 2 to sink 2, there's one path. From source 2 to sink 3, there's one path of weight beta. From source 2 to sink 4, there's one path of weight beta squared, etc. And this graph, just like the one above it, is periodic. So whatever we've done here, we really can do there and there and there. So everything is going to be the same, just shifted by 1. All right. Now the tricky part is that the Toeplitz matrix of 1 gamma, gamma squared over 2, gamma cubed over 3 factorial, etc. This is the path matrix of so these are the coefficients of exponential gamma x as a power series. Alright, so we've got all these horizontal edges with oriented from left to right. And then I have one edge here weighted gamma. And I'm going to draw two edges weighted gamma over 2. And then 3 edges weighted gamma over 3. Then I'm going to continue making this triangle. So this is not a periodic planar network, because what happens on some interval from 1 to 3 doesn't look like what happens on the same on the interval from 2 to 4 shifted. So let's try this. So the path matrix is the 1, 1 position will have a 1 because there's one path from source 1 to sink 1, weight 1. From source 1 to sink 2, we've got a single path of weight gamma. From source 1 to sink 3, we've got a single path of weight gamma times gamma over 2. So that's gamma squared over 2. And then from source 1 to sink 4, we've got a single path of weight gamma times gamma over 2 times gamma over 3. So that's gamma cubed over 6. Etc. So it's actually kind of easy to see that the first row is going to turn out to be the coefficients of this exponential generating function. Exponential of gamma x. Now we want the second row to be the same thing but shifted over, which maybe doesn't look like it's likely to happen because when we start at 2, the picture doesn't look anymore like it did when we started at 1. But let's try it anyway. So from source 2 to sink 1, there's 0 paths because this edge is oriented downward. From source 2 to sink 2, there's 1 path because we just go straight across and it has weight 1. From source 2 to sink 3, there's 2 paths. Each one of them has weight gamma over 2. So we add those weights together and we get gamma. Sort of magically getting the same answer that we got there. Now from source 2 to sink 4, let's see how many paths there are. There's 1, 2, 3 paths. And each of the paths has weight gamma over 2 times gamma over 3. So we've got a sum of weights of paths, which is 3 times gamma over 2 times gamma over 3, which is gamma squared over 2. Again, miraculously the same as what we got here, even though what we're doing is different. And then I guess I don't have enough edges to check the next one. But let's go from source 3. From source 3 to sink 1 or 2, there's 0 paths. Just there aren't any paths. From source 3 to sink 3, there's 1 path of weight 1. From source 3 to sink 4, there's 3 paths. Each of the paths has weight gamma over 3. So 3 of them add up together to get gamma. And it turns out that we actually get this Toeplitz matrix by taking the path matrix of this planar network. Now actually I've never seen a proof of that written, and I was never careful to really finish the proof by myself, but I think this is how it works. So this proof is not written anywhere as far as I know. So maybe I should have called this proof idea because those details are not all worked out. But I think that's how it goes. Now, the exponential power series doesn't have any zeros or poles. So if we're studying zeros or poles, this part doesn't even really come in to the calculations. But let's look at an application to polynomials. So a corollary to the theorem is that a polynomial of the form 1 plus a1x plus a2x squared, etc., let's say it has degree d, has only real zeros if and only if the Toeplitz matrix 1 out a1, a2, etc., up to ad is totally non-negative. And the proof is, well, this follows from the Aissen-Schoenberg-Whitney theorem. I should say it's the special case of the theorem. With all the parameters beta equal to 0 and gamma equal to 0 also. So let me do an example of using this theorem. So I claim that the polynomial 1 plus 6x plus 5x squared plus x cubed has only real zeros. And my proof is that the matrix 1, 6, 5, 1, 1, 6, 5, 1, 1, 6, 5, 1, etc. So that is T of 1, 6, 5, 1. Is the path matrix of the planar network so all my edges are going left to right. So I have this column of very slanted edges, and then I'm going to have some more horizontal edges, so I'll sort of make an X out of these. And then in between the legs of each X, I'm going to draw another edge this way. And then above the two arms of each X, I'm going to draw an edge up that way. And just keep this going forever. And now if we count paths to form the path matrix, from 1 to 1 we've got one path, and there's no weights here, everything's just weighted 1. So there's one path, so that explains the 1 here. From source 1 to sink 2, or for that matter any source I to sink I plus 1, we want to get a 6, because that's what's in the I plus 1 position for all I. So let's see, so there's 4 places we can go down. If we go down one of these 2 times, then we get to the middle of the X and we have 2 choices of how to continue. So 1 choice, 2 choices, 2 choices, 1. So that's 6 ways to get from source I to sink I plus 1. So that explains the 6. Alright, now there should be 5 ways to get from any source I to sink I plus 2. Oh brother. So let's see if we can find them. So I guess we could take the first possible path every time we have a choice. So alright, so there's one way to get from source 1 to sink 3. And then, so taking this edge, oh, that wasn't the first possible because I could have gone down this way. Actually, there's 2 more. I can take this little edge and then I can take either part of the X. So let's see, I can go this way and then down and then over to that part of the X, and then let's say I take the leftmost one and then I go straight over, or I can take so this is supposed to be going down that part of the X. This part of the X is not available because it's too far to the left. And then when we get here, we'll take that leg and over. So now we've got 3 ways to get from 1 to 3. And if we go down this edge, I think those are the only 3 possibilities. Now let's say we go down that edge. So maybe a dotted black line. Now if I want to get down to 3, I guess I have to take the left leg of the X, because otherwise I'm going to be too late. This gets down too late to hit that edge going down. And once I go down the right leg, then it just can't get to 3. So I can do that, and I can take the right arm of the x down to that same middle point, left leg, and make it over to 3. Again, I can't take the right leg of the x because that gets down to this level too late to go down one more level. And of course we can't go here because that gets to this level much too late to get down to that level. So there's 5 paths from I to I plus 2. That explains the 5 here. And then there should be 6 paths to get from source I to sink I plus 3. There should be 1 path to get from source I to I plus 3. And let me do that maybe from 2 to 5 because I haven't messed up the picture there yet. So I think if we take the earliest possible path, we'll find it's the only one. So here, go down as soon as possible, and then over there, and then down as soon as possible, and then over there. And that is, if we take every leftmost choice, whenever we have a choice, that just barely gets us to 5. There's no other way to do it. So that explains the 1 in the 4th position of the first row, or the I plus 3 position of any row. Now, if we knew the zeros of the polynomial, okay, well that's the end of that proof. If we knew the zeros of the polynomial, we could factor this as 1 plus alpha 1x, 1 plus alpha 2x, 1 plus alpha 3x. Then we could write a planar network where we have alpha 1 edges, and then alpha 2 edges, and then alpha 3 edges. So these are all weighted alpha 1, all weighted alpha 2, all weighted alpha 3. But that wouldn't really make sense as a proof that this has real zeros, because we would need to know what the zeros are in order to use this proof, which we wouldn't need the proof if we already knew what the zeros were. So that suggests a question. How can we find the right planar network if we don't want to use the zeros? If we're trying to prove that the zeros are real, we don't know what they are. How can we find the right planar network for a polynomial? And the answer is trial and error. So there's no general method known. And if you're wondering how did I come up with the planar network, that I used for the solution of this claim, well, I cheated. I drew the planar network first, and then I came up with the polynomial afterward. The end.